we're going to learn how to graph complex numbers, but before we begin, it's very important to know that when we graph a complex number, we will no longer be on the coordinate plane. It will look like the coordinate plane, but it's really not. So our objectives, we're going to graph complex numbers in the complex plane as points and as vectors. We're going to convert between standard form of complex numbers and their vector notation. We're going to find the argument and modulus of a complex number, and we're also going to find magnitude and direction of vectors in the complex plane. So the complex plane has a name, okay? The complex plane is called the Argand diagram. Okay, so it is going to be made up of a horizontal axis and that's going to be the real axis, and it's also going to have a vertical axis which will be the imaginary axis. All right, so a complex number, which we said was a plus bi, so remember this is a complex number, has two parts. It has a real part, which was a, an imaginary part, which remember we said was just b, does not include the I, it is just b, right? So since it has a real part and an imaginary part, those two parts are going to determine the ordered pairs. Instead of having x's and y's, we have a comma b instead of x comma y, where a is on the horizontal axis and b is on the vertical axis, okay? So to graph a complex number, you graph it according to its associated ordered pair. Okay, so for example, if you have 4 plus 6i, your ordered pair would be 4 comma 6. So 1, 2, 3, 4, 1, 2, 3, 4, 5, 6. There you go. You have just graphed 4 plus 6i. Awesome. Okay, so there are some other really important numbers that are associated with a complex number, and it's related to the graph of a complex number. So we're going to talk about those important numbers. The first number that I want to talk to you about is the absolute value of a complex number. So it looks like this, a plus bi with the absolute values symbols around it, okay? The absolute value is also called something else. It's also called the modulus. Modulus, okay? So when they say modulus, this is what they're looking for. They're looking for the absolute value. Okay, so it is represented by this formula. The square root of a squared plus b squared. Okay, so what is that? What does this tell us? What is this number related to the graph? Well, the graph of a plus bi, okay, a plus bi is a certain distance from the origin. It's a certain distance from the origin. And that distance, remember distance is absolute value. So it is that distance. This is the modulus, or the absolute value, is this measurement right here. Okay, so that's what the modulus, or the absolute value, tells us. Okay, another important number that we're going to talk about now, other than absolute value, is called the argument. Okay, and the argument is the angle from the positive real axis to the terminal ray that passes through the graph of the complex number. Okay, so it is this angle right here. Okay, well, this is a triangle, so using trig, we can figure out that this angle, this theta right there, is going to be equal to the tan inverse of b over a. Okay, since this is a and this is b, right? Here's a, here's b. We want to know this. So tangent of this is b over a. So theta is the inverse tan of b over a. So we have a nice little formula here. Okay? So the argument and the modulus, two very important numbers. Let's just try some examples. Let's do an example 1 where we just want to find the modulus of 3 plus 3i. Okay, so formula 3 plus 3i is equal to square root a squared plus b squared. So that's the square root of 3 squared plus 3 squared, because both a and b are 3, right? So that means it's the square root of 18, right? Done. All right. So here's something that we also need to know. Let's say that this 3 plus 3i here's its terminal ray. This 3 plus 3i, let's say that it had an argument of pi over 4. All right, cool. Pi over 4. However, it could also have an argument of 9 pi over 4. Okay, so remember we talked about coterminal angles. They're always equal. So in order to get more angles, all you have to do is whatever your argument is plus 2 pi. Okay, and you can keep going and going and going. In fact, you can go on forever for infinity, right? Infinite arguments. Okay, but for the sake of our sanity, we are going to limit between our arguments between 0 and 2 pi, right? So it couldn't be 9 pi over 4 because we have the interval between 0 and 2 pi. So that's what's going to help us. That's what's going to help us define the exact argument. Okay, so let's talk about something else.
Howdy. You mind if I push this?
It's okay. Let's talk about what makes two complex numbers equal. Okay, so the conditions for equal complex numbers. Okay, condition number 1, their modulus has to be equal. So plural would be moduli. Okay. Second condition, okay, their arguments are equal. Okay. However, because you can have infinite arguments, as long as the arguments differ by multiples of 2 pi, they're fine. Okay, equal, differ by multiples of 2 pi. Okay? So let's talk about numbers. And complex numbers can be represented by graphs called a vector. Okay, so a vector is a directed line segment, and it's like a ray, okay, because it has direction, but it has a length or a magnitude, right? Because remember we had the modulus. So a vector is like array, okay, because it has direction, but also has magnitude. All right? And the magnitude is the absolute value, or modulus, right? Okay, so a vector will have an initial point and a terminal point, and a vector in standard position has an initial point at the origin, okay? And when you draw a vector, you're only going to use half an arrowhead. So instead of making an arrow, it's only going to be half an arrow, okay? That's how you'll know it's different between a vector and a array. All right, so let's say we want to graph the vector for the complex number -2 plus 3i. So let's go ahead and put in position, so -2 and 3. So now we've got our initial point and our terminal point, okay? So we'll go from, this is in standard form, and so all we have to do is add the arrow, and we have graphed it. So in order for vectors to be equal, they have to have same magnitude and same direction. However, so same magnitude, same direction. However, they do not have to be both starting at 0. So I could have a vector over here, and as long as it has a width of 2 and a height of 3, and it's going in the same direction, then it's an equal vector, okay? Let's talk about some symbols, okay? Symbols for vectors include a half arrow, so like this, U with a little half arrow, or a bold letter. So if it's bolded, it's a vector, okay? I think your textbook is going to use the bold, okay? The coordinates for a vector, instead of doing an ordered pair, you're still going to use A and B, but you're going to use these types of brackets instead of parentheses, okay? So that's how you're going to distinguish when you graph a complex number and you want to know, do I graph it as a point or do I graph it as a vector? Well, if it's like this, -2, 3, you're going to graph it as a point for a complex number. However, if it's written like this, you're going to graph it as a vector for that complex number. Okay? All right. Let's do an interesting problem. A graph for this problem. And we have a vector, and its magnitude is 16, and its argument is 5 pi over 6. Okay, so again, that's super important to know, right? So we know that its modulus is 16, and we know that its argument is 5 pi over 6, okay? But we need to find the complex number. Find complex number. Okay, so we're going to have to do some algebra, okay? First things first, okay, we know that inverse tangent of theta is b over a, okay, which means that inverse tangent of 5 pi over 6 is equal to b over a. Okay, so that's nice. All right. So when it says I'm sorry, not inverse tangent. That doesn't make any sense. I didn't even, okay. So theta is equal to inverse tangent of b over a, okay? However, so if theta is equal to the inverse tangent of b over a, that tells us that tangent of theta is equal to b over a, right? So that means that tangent of 5 pi over 6 is equal to b over a. Okay, so that's helpful. And so tangent of 5 pi over 6, you have to use your chart. And your chart says that tangent of 5 pi over 6 is negative 1 over the square root of 3. Okay, so I'm going to go ahead and solve for let's go ahead and solve for a, okay? So that means that a is equal to negative square root of 3 times b, okay? And this is important, all right? Even though it's still not solved completely because we have a b, it is kind of important. All right, so we also know that r is equal to the square root of a squared plus b squared. Well, we know that a is this, so we can go ahead and write that in. A is negative square root of 3, we're going to still have to square it, plus b squared. Oh, sorry, negative 3b squared. Okay, so that means r is equal to, well, negative squared will become positive. The square root of 3 squared will become 3, and then we'll have b squared plus b squared, and it's still square root. So r is equal to 3b squared plus b squared is 4b squared. Okay. Good so far. And r, we know, is equal to 16. And then the square root of 4 is 2, and the square root of b squared is b, which means b is 8. All right, we've got an actual number, okay? So if b is 8, that means a, we can plug that back into here, that means a is equal to negative square root of 3 times 8. So a is equal to negative 8 square root of 3. So we've got an a, we've got a b, complex number, so negative 8 square root of 3 plus 8i. All right, that's it. Going to 7.2, 2 through 6 evens.